Hello everyone. Today, I'm honored to deliver my speech at the EEI ChinaCom 2021 conference. The title of my paper is Text Error Correction Method in the Construction Industry based on Transfer Learning. And I will give a speech on this paper from the following four parts: background, proposed method, experiments, and conclusion. In recent years, with the development of the construction industry, the building construction scheme is also transitioning from paper to electronic, but it also brings about the problem of text errors in the scheme. These errors reduce the readability of construction industry tests. Therefore, it is of great value to automatically detect and correct the content of construction industry tests. Currently, there are many methods for correcting errors in Chinese tests. Traditional Chinese text error correction technology first uses rules, statistical models, and other methods to check errors, and then perform error correction. However, these methods have low accuracy and other problems. With the development of deep learning, various neural networks emerge in an endless stream, among which there are many models applied to Chinese text error correction, such as BERT, LSTM, transformer self-attention, circle-to-circle attention. The BERT model is a deep learning language model with strong generalization ability and high accuracy among the current text error correction models. Therefore, more and more scholars use the BERT model to perform text error correction. That is, first perform unsupervised training on a large amount of unlabeled data corpus, which can learn a lot of priori language, syntax, word meaning, and other information, and then use the learned features for downstream tasks. However, for construction industry tests, which are compound tests with multi-domain provenance, the lack of labeled data leads to poor error correction algorithms based on deep learning. So, we base on the BERT model and adopt the transfer learning method. After learning from the dataset of other related fields, we retrain the model. Then, let me introduce the BERT model. The BERT model architecture is divided into three layers: embedding layer, transformer layer, and prediction layer. Unlike traditional models, BERT uses bidirectional transformers as the feature extractors for the language model. A large number of studies have shown that the two-way language model has a more accurate understanding of semantics during training than the one-way language model. With the emergence of MLM technology, the training of two-way language models was started. Since the goal of BERT is to generate a language model, BERT uses the encoder part of transformer. The highlight of the BERT model is focused on the task part of the pre-training process, including two unsupervised prediction tasks, MLM and NSP. The MLM task is similar to close-filling for the input tenants. 50% of the tokens are randomly masked, and the masked tokens are predicted by an unsupervised learning method. The essence of the NSP task is a binary classification task. In the pre-training process of the BERT model, the model receives paired sentences, such as A and B, as input, and then predicts whether B is the next sentence of A. There is 50% probability that B is the next sentence of A, and 50% probability that B is a random sentence in the corpus. When training the BERT model, in order to minimize the combined loss function of the two tasks, we jointly train MLM and NSP. The loss function is defined as this, where theta is a parameter of the encoder part in the BERT model. Theta1 is a parameter in the output layer connected to the encoders in the MLM task, and theta2 is a classifier parameter connected to the encoders in the NSP task. However, in the field of text error correction, we can achieve the same word order correction ability by removing the NSP task in the pre-training stage of the BERT model. Therefore, this paper introduces the pre-training coefficient lambda, dynamically adjusts pre-training tasks at different stages, and defines the following optional loss function. After the pre-training is over, we get the BERT pre-training model. Then, fine-tuning is performed on the basis of the BERT pre-training model. We focus on 4 types of text error in the text error correction task in construction industry tests: missing word completion, redundant word removal, word selection correction, and word order correction. In our work, we use 41 building construction scheme documents from the construction industry, containing a total of 9,070 sentences. These sentences cover proper nouns in different fields, including geography, geology, chemical materials, construction equipment, building regulations. We select 5,400 representative sentences and divide them into 5 groups, each with about 1,000 sentences. No modification is made to one of the groups, and the other 4 groups are artificially modified according to the above 4 types of errors. We name this corpus as a construction document corpus dataset and regard it as a target dataset, which is used to verify the model's ability in text error correction in the construction industry. Since the target task has fewer datasets and is rich in proper nouns from different fields, we try to use the unlabeled data of related fields by transfer learning, and fine-tune the parameters through training to make the model get the ability of vocabulary recognition closer to the target task. We select 1,538 professional documents in 5 fields, including geography, geology, chemical materials, construction equipment, and building regulations from Chinese literature databases such as CNKI and Wang, with a total of about 420,000 words, forming an unlabeled related field dataset. In this paper, we use a pre-trained BERT model based on Chinese corpus and adopt the progressive transfer learning method. In the first stage, we apply the pre-trained BERT model of massive Chinese corpus to the unlabeled related field dataset, so that the model can obtain vocabulary information from different subdivision fields. In the second stage, we use the training samples in the construction document corpus dataset for the retraining of the model after transfer learning, make it more targeted at construction industry tests involving multiple fields, and improving the ability to detect and correct text errors. After unsupervised training on a large number of unlabeled related field datasets, the ability of MLM has been significantly improved, and it can accurately predict proper nouns from different fields in the target dataset. However, since the unlabeled related field dataset is the entire article from each field, the sentence context in the same field has strong relevance. While building construction scheme documents of the target dataset are command documents involving multiple fields, and the upper and lower sentences may come from different fields. In this case, the NSP task of the first stage will have a negative effect. Eventually, the correct word order will be recognized as a word order error. In order to solve the problem of word order positives in our proposed model, we make choices on the NSP task at different stages. In the first stage, where unsupervised training is carried out using unlabeled related field dataset. For loss function, we set lambda equals to 0, which removes the NSP task, and only train MLM to strengthen the model's learning of proper nouns in different fields. At the same time, it ensures that the model is not affected by strongly related sentences in the same field. In the second stage, for loss function, we set lambda equals to 1 to unlock the training of NSP. After the fine-tuning training of the target dataset, the word order false positive rate of the model can be effectively reduced. For the division of the dataset, we set 70% of the construction document corpus dataset as a training sample set, and the remaining 30% as a test sample set. First, we experimentally compare our model with commonly used deep learning text error correction models, such as LSTM, transformer self-attention, circle-to-circle attention. We conduct experiments on the following four models through the test samples in the construction document corpus dataset. From the table, it can be seen that the transfer learning method proposed in this paper has a high precision rate than the commonly used deep learning text error correction model. Then, we perform ablation experiments with our model and the other three models. The three models are: after freezing the parameters of the pre-trained BERT model, we apply it directly to the targeted text error correction task, set to M1. After fine-tuning the pre-trained BERT model through the training samples in the construction document corpus dataset, we apply it to the targeted text error correction task, set to M2. The pre-trained BERT model freezes the parameters after the transfer learning of the relevant field dataset, and we apply it directly to the targeted text error correction task, set to M3. It can be seen from that our proposed method significantly improves the ability of the text error correction task of the target dataset. It can be seen from A that because there are more proper nouns from different fields in the target dataset, if the pre-trained BERT model is used for text error correction without other operations, FPR will be as high as 90.8%. If the model is fine-tuned by the target dataset, FPR will drop slightly. This is because the target dataset has fewer training samples and the training effect is not ideal. After the transfer learning by unlabeled related domain dataset, the BERT model learns a large number of proper nouns from different fields. Then we fine-tune the model. The FPR of the model drops significantly, only 9.7%. From B and C, it can be seen that the model after transfer learning and fine-tuning improves the error location and error correction capabilities, which which is reflected in that compared with the pre-training BERT model, our model improves the precision rate by 13% and the recall rate by 12.8%. In addition, from the experimental comparison between M2 and M1 and the experimental comparison between our proposed model and M3, it can be inferred that fine-tuning for the target dataset is very important. The comparison of the experimental results of M3 and M1 shows that transfer learning of unlabeled related field dataset has a significant improvement in the effect of text error correction tasks, which shows that transfer learning greatly improves the situation of lack of target dataset. Finally, in order to verify that our method makes significant progress in the word order correction task of the target dataset, we conduct an experimental comparison of the following two models: the model which removes the NSP task in the first stage after transfer learning and fine-tuning, and the model which reserves the NSP task in the first stage after transfer learning and fine-tuning. And we use false positive rate as an evaluation indicator of the word order correction task. We classify the experimental results according to different types of test error and get the false positive rate of the word order correction task. Compared with M4, the false positive rate of our model in the word order correction task is reduced by 1.8%, which shows that removing the NSP task can effectively reduce the word order false positive. The last part is the conclusion. This paper proposes a text error correction method in the construction industry based on transfer learning. On the basis of the pre-trained BERT model, we perform transfer learning through unsupervised training of unlabeled related field dataset, and then use the training samples in the construction document corpus dataset to retrain the model after transfer learning to complete test error correction task. At the same time, we dynamically adjust the pre-training task in transfer learning to improve the performance of the word-order correction task. Finally, experimental results show that our proposed model has higher precision rate, recall rate, and a lower false positive rate in the error correction task than other models. Thank you for listening.